This trig class wouldn't be complete without an introduction to polar coordinates, and that's the last lesson that we will be learning here. So polar coordinates, they describe any point in the Cartesian plane, x and y. Remember, it's just the x-axis and the y-axis. But rather than going over so many units and up y units, what they do is they describe some point, P, that's a certain distance r from the origin, and it has a particular angle that corresponds to that. And the way that they describe each point is you do your r first, so you list the distance from the origin first, and then where it's located. We get so used to the XY plane, but there are different ways to describe where you're located, and this is a great example. And then, so that's the first point, and that's R, and then this is the second, theta, would be the angle where you're located at. So it's just kind of a neat thing to think outside of the box. It's helpful when we're dealing with angles and trigonometry because it's so convenient. We oftentimes just deal with various angles and trig ratios. So it's a really cool thing. So we're just going to explore this today. What they're showing here is you take this point P, and if I wrote it, if you come up with R, so R is going to be the same value, but now it's the opposite of R. What it tells you to do is you go up to theta, whatever theta is, because it's the same angle theta, but then rather than landing R units away here, which would be this spot, I'm going back through the origin and R units away in the opposite direction. So by doing this, we're covering all the points in the XY plane as well, but on a polar coordinate scale. So the book actually doesn't ask you to graph these, it just wants you to convert these from a polar form to a Cartesian form. So what we're going to do is we're going to just graph them because I think it's so helpful to visualize where this is, because every polar coordinate has an equivalent Cartesian coordinate. And we'll talk about that in a second. So an x and a y. Okay, so what you do is you look at the angle first, 210 degrees. That's why I never understood. I think they should have listed the theta first, in my opinion. So you go to 210 degrees, and it's just positive, so I'm going all the way around to here. And then how many units am I from the origin? I'm 6 units. So on this line here, start in the center, you go 1, 2, 3, 4, 5, 6 units away from the origin. So that was 1, 2, 3, 4, 5, 6 units. So this point right here is 6, 210 degrees. Just for practice, what would negative 6, 210 degrees be? So let's write that over here. Negative 6, 210 degrees. Well, we would go around to 210 degrees, and then I'm going to follow this line back through the origin. If I did this correctly. If you wanted to just double check, you know you're 2 ticks away, main marks away, so you should be 2 main marks away, so you're going to be at 30 degrees. And then from there I'm going to go, so instead of being at positive 6, it's negative 6. So that tells me I go to this spot and then I go through the origin and back 6 units. So it's 1, 2, 3, 4, 5, 6. So this point is negative 6, 210 degrees. So you keep the same angle, and that's the confusing spot. You keep the same angle because you have to start over here, and then you go through the origin to negative 6. Now what is this equivalent to? Well, we could also call this a different point because these polar coordinates, they're not actually unique. So this is the same as, well, this is 30 degrees, and it's 6 because it's 6 units away from the origin at 30 degrees. So these are equivalent points. So just something to think about. Now with number 2, 3 pi. So remember, and polar coordinates can be in radians or degrees. So here is 2 pi, going around one full rotation, 2 pi radians. So 3 pi would land me right on the x-axis over in the negative direction. So I'm here, and instead of going over 1, 2, 3, 4 in this direction, I'm going over 1, 2, 3, 4 units in this direction. So the point is actually over here, negative 4, 3 pi. Now I want you to stop and think about what an equivalent point might be. So can you think of an equivalent point? Okay, so 4 would be 4 units from the origin, and this angle right here could be 0 degrees. It could be 2 pi, it could be 4 pi, any even thing, but the positive 4 would land you there. So let's look at the third point, 2 and 11 pi over 6. Well, 11 pi over 6, here's 1, 2, 3, 4, 5, 6. No, I broke it up too many. Here's pi over 6. They gave us too many options. So 1 and then 2, 3, 4, 5, 6. Here we go, 7, 8, 9, 10, 11. So this is 11 pi over 6, 330 degrees. And you can always look at the unit circle. And from there, we are 2 units away, 2 units away from the origin. So this point right here is 2 comma 11 pi over 6. Pretty cool, huh? Okay, let's look at 6 and 90 degrees. That lands us at, let's see, so 90 degrees is up here, or you could say this is equivalent to 6 if you saw it as pi over 2. That would be the same thing, right? And then from there we're 1, 2, 3, 4, 5, 6. So this is 6 pi over 2, or 90 degrees. And then the last one, negative 1 and 405 degrees. Well, 405 is all the way around at 360, plus you're going 45 more degrees. So this is 405 degrees as well. Okay, that's after one extra rotation. But since it's negative 1, if you follow this line down to the origin, it's negative 1, so that would land you negative, you have to go through the origin and back out this way. So we are here, and we're getting a little sloppy, but this is 45 degrees. You know, it's halfway in between 180 and 270. So we're going to go 1 unit from there, follow that line. So that would land us right there. So that would be, let's see, negative 1, 405 degrees. Now let's use one of these simple points to actually find what the equivalent xy Cartesian coordinate would be. How about this one? This one's pretty simple and straightforward because I know I could actually count. Think of now laying the xy plane directly on top of this because it is the same idea. So the xy plane here, here's the origin, here's 0, 0. I'm 6 units up. Imagine this is your x-axis and this is your y-axis. So the equivalent point to this is actually just going to be 0, comma 6. So your x value is 0 and your y value is 6. Okay, now I want to show you some graphing because coordinates or polar equations are beautiful to graph. Okay, so I went to Desmos again, lovely Desmos, and I move this up so you can see desmos.com. And you can do this in your graphing calculator. You have to go into mode and then change it to polar. But I just think it's so much nicer on Desmos. So we're going to go to graph settings. You want to change it to a polar grid. Okay, you can close that up. And then the function I'm going to graph and we're going to play around with is r equals 2 cosine 2 theta. You can just type in theta and it'll automatically go. It's so nice. And you have to graph number 15, so you can use Desmos or a graphing utility, whatever you want, to just sketch the graph. I wish we had more time to get into that, but hopefully you will see that. Well, you'll definitely see this again in pre-calculus and then also in calculus. So you can see it makes this beautiful, lovely flower looking thing. And if you play with the different angles inside, you start off with like a circle, and then you got the flower, and then you've got like flower with three petals, and then you can get multiple petals. So I'm just playing around with the different angles. And then this out here, how does that affect it? Well, we've got, ooh, it makes it bigger, bigger, prettier flower. So I'm going to go back to this one because I actually copied and pasted it into my drawing program. And we're going to explore points and finding Cartesian points from this graph. Okay, so just playing around with this graph, and this is our function, r equals 2 cosine 2 theta. This point in the xy plane, so the xy coordinate of this is just 2, 0. But the r theta coordinate, the polar coordinate, well, you know that theta is 0, or it could be 2 pi or 4 pi or any even pi, and the radius is 2, meaning, I say radius, but the distance from the origin is 2 units. So it's pretty easy to identify these. We could do this point, the xy point is 0, 2, and the equivalent polar coordinate would be it's 2 units away from the origin, and the angle is pi over 2. We could also say 90 degrees if we wanted to be in degrees. But what about a point like this or this? Let's start with this one. The polar coordinate of this would be, we'll see the angle is pi over 3. It's on this line. So I would say pi over 3. And then how many units is it? Well, according to the scale, it's 1 unit away from the origin. And if I were to be in degrees, that would be 1 comma 60 degrees. Okay? So either or would be okay. So if I asked you to go from polar to coordinate, or Cartesian, that's the Cartesian coordinate, the xy. So we're going from r theta to xy. Now remember, I could line up the xy plane in here, and if I could figure out how far this is, this distance, x units over and y units up, I would be set. Well, that's where our fun trick comes in. So we're going to drop down a perpendicular here. You guys sick of these reference triangles? You shouldn't be, because we're going to use them a lot and they're very handy. Hopefully you have an appreciation of them. So do you see that this angle right here, this is theta, and we know that theta is equal to 60 degrees. So I can say that this angle right here is 60 degrees. What else do I know about this? Well, I know that the distance from here to here, the hypotenuse of this right triangle, is 1 unit. Okay? I have one side and I have one angle. Can I find this side x and can I find this side y? Yes, that's chapter 1, and that's why I love tying it all together. So the cosine of 60 degrees is equal to adjacent, which is x, over 1. Okay, so if I brought the 1 over, and I'm going to leave it like this just so that you guys can see, 1 cosine 60 degrees is equal to x. Well, the formula for converting from polar to Cartesian is just this. It's r, and remember that was the distance from 0 to your point, and that's given in polar form. Cosine of theta, that's equal to x. So do you see this, the similarities? And if we think about the unit circle, cosine of 60 degrees, well, remember where that is. Cosine of 60 degrees is equal to 1/2. So we can say that this is equivalent to, let me just go down here, 1 times 1/2. So this point right here is x equals 1/2. Okay, and you could type that into your calculator, that's fine. So this right here is equivalent to 1/2, and now we need to find y. Well, y, it's the same way. We can say that the sine of 60 degrees is equal to opposite leg over hypotenuse. So that's 1 sine of 60 equals y. And that's the general formula. 1 was r, sine theta is equal to your y coordinate. Isn't that cool? So that implies that y is equal to the square root of 3 over 2, because that's sine 60 is root 3 over 2. You can check it on your unit circle. But root 3 over 2. And so now this point is 1/2 square root 3 over 2. So here it is summed nicely. If you're going from a polar coordinate to a Cartesian coordinate, you know that x is equal to r cosine theta and y is equal to r sine theta. Remember that the y in the unit circle is always associated with the sine theta, so that's how I remember that. And the x is always goes with cosine theta, so that's pretty easy. If you're going from Cartesian to polar, meaning like an xy point to an r theta point, you can find it, it's just like the complex numbers. It's plus or minus x squared plus the square root of x squared plus y squared, because that's the hypotenuse. See, this part is x squared plus y squared, take the square root of that. And then the tangent of theta would be y over x, which is this right here, this ratio, tangent theta opposite over adjacent. And so that's how you find, if you know theta and if you know your radius, you can find x and or actually, sorry, if you know your x and your y right here, you can find theta and you can find your radius, and that would give you the polar coordinate. So let's do one of those examples. Okay, so if you're doing this, and I just chose some examples from the book, I think it's helpful to think about where this is. And so remember, we're in polar and we're trying to get to Cartesian. So you have to go to 3 pi. So you're going around, here's 1 pi, 2 pi, 3 pi. So that lands me right on the x-axis in the negative direction. But because of this -4, rather than 4 units away, because this point would be 4 comma 3 pi, I'm actually go back over here to -4 units. That tells me go through the origin 4 units. So it's -4, 3 pi is right here. All right, so I'm going to do this even though this one would be obvious. This point right here is going to be 4 comma 0, just because I know that I'm 4 units away from the origin and the y value is 0. If you didn't know that, you can just use the formula. So x is equal to, so in this case, maybe identify r is equal to -4 and theta is equal to 3 pi, and just plug it into this formula, 6.9. So from 6.9 we can say that x is equal to -4 cosine of theta, which is 3 pi, and y is equal to -4 sine of 3 pi. So cosine of 3 pi would land me at -1, because that is over here, and that's the x value on the unit circle, which is -1. So that would be -4 times -1, which is +4. Okay, so that gives you that x value right here. So our x, y point, is going to be 1, or 4, excuse me. And then we know that the sine of 3 pi, well, that's on the unit circle back over here. 3 pi, or any pi, odd pi for sine is 0, because you're not going up or down. So it would be -4 times 0, which would give me 0. So that's why we get that point. Okay, now we're going from Cartesian to polar, and you can still figure out where your polar coordinate is, what quadrant it'll be in, by graphing this point. So 1, 2, 3, and up 1. Okay? So you can see, I mean, rather than memorizing formulas, I would just calculate, what is this distance? Well, I know that I'm over 3 units and up 1. But do you see how it's this right here? And we don't need to worry about the negative because we're not on this side. We're gonna stick with the positive coordinate. So that means I need to find an angle. Theta is going to be in quadrant 1 as well. So you have to think about where theta is by your point. Okay, so by Pythagorean theorem and by this formula, I know that r is equal to the square root of 3 squared plus 1 squared. That is 9 plus 1. That's the square root of 10. So that's r. Okay, so I've got my square root of 10. I don't have my theta. And to find that, we can use this. And once again, that's just a triangle. That's tangent. Here's theta. So it's tangent of theta is equal to opposite leg over adjacent leg. So just kind of pay attention when you use your calculator. If you want to be in degrees or radians, I would just choose degrees. So we're going to do tan inverse because we need to find the angle. Tan inverse of 1/3, and that would give me a theta of 18 point, went away too fast, 18.4 we can say, which makes sense in this region, right? That it's in the quadrant 1. So we can say 18.4 degrees. And that's how you go from Cartesian to polar. There are a bunch of examples in your book as well, but that should give you enough. I would always say plot it because I think the visual is nice and it's a good way to check your answer. So remember what this means, that you are going to find this point. You go rotate theta 18.4 degrees and you're square root 10 units away, which is a little over 3 units away from the origin. Okay, so a couple of questions. They want you to write a given equation from the Cartesian plane to polar coordinate form. And so what you can do is remember that x equals r cosine theta and y is equal to r sine theta. So I'm going to substitute those values in first. So I've got r cosine theta, and that's squared, minus r sine theta, and that squared equals 1. I put up here number 11, see example 6.18. So that's writing a given equation in polar coordinates as well. That'll help you with number 11. It's very similar to 6.18. Okay, so now, and I'm doing number 13 for you, and that was the assigned, so you just have to write it down and see if you understand it. So this square has to go to each of the r and the cosine. So if I square cosine, I just write it as cosine squared theta minus r squared sine squared, oops, I forgot to put the square there because I'm squaring both, as I said, theta equals 1. Now it's just kind of playing with a little algebra. So if I factor out, you can see that r squared is a common factor. I'm left with cosine squared theta minus sine squared theta. It's not always obvious, and I know we're learning these things, but sometimes you just have to recognize these trig identities, and this is actually a double angle identity. So this here is equal to cosine 2 theta, and you can look back at your identity chapter to see that. But we've got cosine 2 theta, and then we have the r squared theta. R squared is equal to 1. So the back of the book just writes it like that, and you can leave it in that form. R squared cosine 2 theta equals 1. So now this is an equation that's in polar form. So that just concludes the lesson. I hope it was helpful, and I think it's kind of a fun thing. It shouldn't take you too long to do this assignment. I just limited it to the odds, but if you need more practice, I would definitely do some evens. And look online and Google some fun polar graphs because they get really creative. And just remember that every polar point is actually has an equivalent Cartesian point. And have a wonderful day. That concludes the end of all the lessons for this trig class. We made it to the end of the book, everybody. Thanks for sticking it out. Good work.